Welcome to day 3. We're going to work with sequencing again, but today we're going to look at to see whether they're converging or diverging. Converging means the bigger numbers we put in for n, the closer we're getting to one specific number, like 5 or 2/3 or whatever, or even 0. And diverging means we don't know exactly where it's going. It could go to infinity, but that's still diverging. We need a specific value. So we looked at this formula last week. We're only going to work with explicit formulas. The recursive doesn't work with this, what we're going to do today. And last week we had this formula, a sub n equals n squared minus 3. And we plugged in numbers for n to find whatever term we wanted. And specifically, we did the first 4 terms. So we plugged in n equals 1, 2, 3, 4. And we found the first 4 terms of -2, 1, 6, and 13. Well, today we're going to work with something called set notation. So set notation is just another way to write sequences instead of using an explicit formula. It is based on an explicit formula, but you don't have the whole notation a sub n. So this thing right here, the curly brackets, n squared minus 3, and it says n equals 1 to 4. These are the same as what we did the other day. The bottom number tells me which number I should plug in first, and I plug in every integer from that first number to the top number until the end. And in this case, it was 1, 2, 3, 4. So if we want to represent an infinite sequence, we would make it go to infinity instead. So instead of using the explicit formula a sub n equals or b sub n equals, we could use these brackets to represent a formula, and we're going to pay attention because sometimes we're going to start with at n equals 1, and sometimes we could start with n equals 0. It just depends what's given to us. So the big thing today is looking at converging versus diverging sequences. An idea of a converging sequence is that it must approach one specific number. It must converge to a specific value, 5, 2/3, 0, whatever you need to get. So for these examples, I'm going to see if they converge or not. I'm going to find the first 4 terms. I'm going to also find the 10th term. And I'm really going to use my calculator for all this. I mean, you could do this all by hand by plugging in the numbers. Well, in this case, depends what they start with. Like the first one starts with the number 1. The second one starts with the number 0. The third one starts with the number 1. So for the first one, I had to plug in 1, 2, 3, 4, and then the number 10. But I'd rather use my graphing calculator to figure this all out. It's a lot easier to just put that into the y equals and then do the table. So I set up a little table that I'm going to write on, but I'm going to go to the calculator to do all this work. So here I am in the calculator, and you can see I went to my y equals, and I use that fraction bar. It's a great bar, a key to use. I've typed in 1 over x squared. And I've already set up my table from the last class, so I'm just going to go second table, and there are the first 4 terms. If I want to go see the 10th term, I could just use my arrows and scroll down to 10, or I could plug in 10 if I wanted to, and this is not a hard one to plug in 10. I'm going to go back to where I have x equals 1 because I like it where it's at 1 for future use. So I think you can see as I keep on putting bigger and bigger numbers in for n, I'm getting smaller and smaller and smaller fractions approaching 0, so this does converge to 0. Now this next one, I want to start at n equals 0, not 1, and because I'm starting at n equals 0, the 10th term, I'm going to have to use n equals 9, 1 less. So I'm going to go to my calculator and do all this. So here I am, I typed it in the calculator. I'm going to go to the second graph to see the table. I'm going to have to move it up to 0 because I have to start at 0. And those are my values. Those are the first 4, 0, 3, 2, and 9/5. I can move it down to 9 to see that result. And then I want to see if it converges or diverges. I'm going to turn this off and put a big number in for x or n. So it's going to be 3 times, let's try 100, over 2 times 100 minus 1. And I could turn that into a decimal, and I get about 1.5. So maybe it's going to converge to about 1.5, but let's see what we got. So I completed this table, and my conjecture is that it is converged to the fraction 3 over 2. 1.5 is 3 over 2. Why? Well, let's see what we have. Let's look at the original problem. If I do leading term over leading term, I see I have 3n over 2n. Oh yeah, that is 3 over 2. So if I would graph this as a function, it would have a horizontal asymptote at 3 over 2, which means the n levels off. And that's what we're looking for. That's what a limit really is. Our converging limit is that the ends level off, in this case positive infinity. So this last one I set up the table that I'm going to write on, and I'm going to go to the calculator and do all the calculations. So you can see I set up my y equals, again I like using the fraction bar, and I can just go to my table, and I got to go back up. Zero's an error, and there we go, at 1, and there's 10, which is 1 over 24, which I'll convert to a decimal when I put in the table. There's 1, and I'm thinking that these decimals are getting smaller and smaller all the time, and it is converging to 0, and it is. And there's the table completing it all, and the decimal is getting smaller, so it is converging to 0. So the idea on the first page, we saw that we put in bigger numbers for n, and the sequence converged to one specific number. And if it does not approach one specific number, then it says it diverges. So a sequence is either going to converge or diverge. There's no in between. And that's what we're going to look at. So when something diverges, it's because we don't know where it's going, or the limit doesn't exist, or it goes off to infinity or negative infinity. That's not one specific number, so it does not converge, it diverges. Even if it goes off to infinity, it is diverging. So again, we're going to do the first 4 terms and the 10th term and see what happens as we put a bigger number in for n. Remember, I always have to pay attention to the value for n that I need to use first. In this case, it's going to be 1. So I'm in the calculator. I use my fraction bar key. I'm going to go to the table. I can see my first 4 terms. I could scroll down to the number 10. I can see my 10th term. I'm unsure where it's going to go, so I'm going to get out of here. I'm going to put in a big number for n. And I'm going to put in 2 parentheses 100 squared over 3 times 100, minus 1. And I get that ugly little fraction, but I could go to hit the math key, hit that little decimal, and convert it to a decimal. That's a pretty big number. I don't think it's going anywhere. So this one diverges, and why does it diverge? I'm going to do that whole leading term over leading term business again. I get 2n squared over 3n. When I look at the leading terms, I get 2/3 n, and 2/3 n is just a diagonal line. It doesn't have a big slope, but it does go up to infinity, so it does diverge because it goes off to infinity. So the next two, you notice one starts at 0, one starts at 1. And I'm actually going to put them both in the calculator at the same time. I'm going to show you how. But I've already made my little tables, and I'm going to go to the calculator. So as you can see, I put them both into the calculator because I can see more than one table at a time. So I'm going to go to second table. I can see both of them right here, and you can see I'm down at the lower values for them. I'm going to bring it up to, well, 1 for y2 starts at 1. That's the one with the fraction in it, and the other one I have to start at 0. And you can see all the values. You could put many equations across, and you would see the whole table if you wanted to. Notice what is happening with y1. If you look at the equation, that equation was at -1 to the n, parentheses n plus 2, and these signs are alternating. So looking at the one in the center, we could see here it's going 2, -3, 4. Oops, made a mistake here. There's my eraser. Can't even find my eraser. This should be -5, and then -11. It's definitely diverging. because not only are they getting bigger, they're kind of alternating back and forth. And we're going to talk about that. In this last one, you can see these numbers keep on getting bigger and bigger and bigger. So even though it's going off to infinity, that's not a specific number. It also diverges. So when we see negative 1 to the n, and we start at 1, it goes negative 1, 1, negative 1, 1, dot, dot, dot. And if we start with n equals 0, it goes 1, negative 1, 1, negative 1, dot, dot, dot. Either way, we're getting alternating plus and minus signs. So that's what negative 1 to the n does. It's not really an exponential function. Like if you did 2 to the n or 1/2 to the n, negative 1 to the n is just kind of plays this back and forth, what I call ping pong. Positive, negative, positive, negative. Okay, we've studied a lot of different types of functions throughout the year. We have to look at the dominance of functions. Which functions are more powerful than other functions? And it's going to help us to decide if something is converging or diverging. So I'm going to put down the list of the order on which is more powerful than the other, and we'll talk about it. Okay, exponential growth is the most powerful function that we've studied all year. I'm going to call he's the king of the hill. He's the most powerful. And obviously 5 raised to the n is greater than 3 to the n is greater than e to the n is greater than 1.5 to the n, and so on and so forth. And remember, I'll change color. Negative 1 to the n is not an exponential. Power functions. Basically, something to the fourth is greater than something to the third is something greater than something squared is greater than n to the first. They do grow, not as fast as exponential functions. The next one is log functions. They grow, but they grow very slowly to infinity. So power function wipes it out. And finally, sine and cosine. They really have no dominance whatsoever, because if you think about the sine and cosine graph, they're stuck between negative 1 and 1. They're called bounded. So how does this help us with convergence? Well, when I do convergence, I'm always going to look at leading term over leading term when I have a fraction. If there's no denominator, I'm just looking at the numerator, and it's probably going to diverge anyways. So sometimes I have the same power function. That's always going to converge to some number. 5, 2/3, a half, 8/3, whatever. Another thing we can have is the denominator dominates. That means the denominator is growing to infinity a lot faster than the numerator. That means it's going to converge to 0. And then finally, if the numerator dominates, it's going to diverge, because the numerator is growing to infinity faster than the denominator is going to grow forever. So this next problem, we're going to do the first 4 terms only. I'm going to do it on the calculator. I'm going to do it quickly. I think you can know how to do the calculator, and then we're going to decide if they're going to converge or diverge, just by looking at leading term over leading term. In fact, I don't think I'm going to put them on the calculator. I'm just going to write them out. If you need help with the calculator, ask questions. I started at n equals 1. I plugged it into the calculator. I got these fractions, and then I did leading term over leading term. I see 2n over 5n, which is just 2/5. So this one converges to 2/5. At some point, it's going to get closer to the decimal point 4. This next one I had to start at n equals 0 because it says here on the bottom. I put it in. It's just 2 to the n. It was really easy to do even without a calculator, and I can see these are growing forever. But even if I did leading term over leading term, it'd be 2 to the n over 1. when the numerator dominates, this will diverge. And I think you can see that it diverges. So for this next one, we have this -1 to the n business, so that's going to help alternate something's going on. And put all the numbers in, and I got the stuff. When I do leading term over leading term, -1 to the n is not really a leading term, so I just call it 1 over n squared. This definitely dominates on the bottom. Therefore, it's going to converge to 0. In this last example, I just did it in the calculator, or actually I might have done it mentally, and I get these terms, and I see 2 to the n is exponential. It dominates over that n squared. They both go to infinity, but 2 to the n gets infinity a whole lot faster, gets a lot larger than n squared. So this one also converges to 0. So now we're going to go the other way. We're going to see what are the patterns for these fractions. And I want to look specifically individually at the numerator and denominator and figure out what kind of sequence I could write for these, what kind of pattern I can see, and determine if it's converging or diverging. So don't get thrown off with the number 1. The number 1 is just 1 over 1, 1 over 1. And when I look at this, the numerator is always equal to 1. My denominator, look at this denominator, it goes 1, 3, 9, 27. Looks like an exponential, 3 to the n. So I think my formula for this is going to be 1 over 3 to the n. And now this is the hard part. This is going to go to infinity. I have to decide what should be my first value for n that I should use to get what I want. Well, what I want is the number 1 to begin with. I'm going to erase some of this a little bit. And then I want 1/3, and then I want 1/9. So if I start with n equals 1, it's either going to be 0 or 1. If I start with n equals 1, I get 1 over 1/3. That's not it. But if I start with 0, I get what I want. And then I notice the exponential is in the denominator. It is going to converge to 0 because the denominator dominates. Okay, the next one. Kind of see the same thing as I had before, but I have this whole alternating business going on. So I know that's going to be -1 to the n, and my denominator is the same as before, which we said was 3 to the n. So I'm thinking this is going to be -1/3 raised to the n, and I'm going to do the same thing. N equals 0 to infinity, and this is still an exponential in the denominator, so this is also going to converge to 0. The idea that it's alternating doesn't matter so much because it's alternating, but it's still getting closer to 0. It's just flip-flopping positive, negative, negative, positive. This next one may be a little bit different. I look at the numerator here, and I see equals 1, 3, 5, 7. That looks very arithmetic to me. If I pay close attention, it's going up by 2, so my formula should be 1 plus 2 parentheses n minus 1. And if I clean that up, I'm going to get 2n minus 1 is the numerator. I'm going to write that down here. 2n minus 1 is my numerator. Now if I look at the denominator, see I have another arithmetic, except it goes 2, 4, 6, 8. So this pattern is going to be 2 plus 2n minus 1. And I can clean that up. I get 2n plus 0, or just 2n. And I'm going to put curly brackets around it. I'm going to have n equals, that one's always infinity. So I have to decide what number do I have to use for n. Well, if I plug in 0, I get -1 on top and 0 on the bottom. I definitely don't want 0 on the bottom. So I think it has to be 1. If I plug in 1, I get 2 minus 1, which is 1, over 2, and that's what I want. Now I have to decide if it's converging or diverging. Well, my leading term on top is 2n, and on the bottom it's 2n. Well, that's just 1, so this one does converge to 1. I look at my numerator. I see another arithmetic one. Except it's going to be 1 plus 5 n minus 1. And if I clean that up, I get 5n minus 4 in the numerator over my denominator. Again, looks arithmetic because I'm adding 8 all the time. So now this is going to be 2 plus 8 n minus 1. I clean that up, I get 8n minus 6 as my denominator. I'm going to put curly brackets around it. And I get n equals to infinity. And I think if I plug in 0, I get -4 over -6. And that's not 1/2. So if I plug in 1, I do get my 1 over 2. Again, when I do my leading term over leading term, I get 5n over 8n. So this one does converge to 5 over 8. And this last one, it's a little bit different. I look at the numerator. I'm like, well, 1, 3, 5, 7, I think I've done that already. If I look at part C, I see it's going to be 2n minus 1 over, I look at the denominator, I see an exponential, and I'm going to say 5 to the n. If I put 5 to the n here, I'm going to have to pay attention to see, am I getting what I want? And equals to infinity. If I plug in 0, I get -1 on top, and if I plug in 0, I get 1 on the bottom. That's good. For the bottom, it's not good for the top. If I plug in 1 here, I get 1 on the top, and I get 5 on the bottom, so I think I have to change this exponent a little bit. And now I can start at 0. Okay, exponential's on the bottom, so I know this is going to converge to 0. But there's another way to write this. Another way to write this would have been, I can see this pattern is going to be 2n because the difference is 2, but I'm going to do plus 1 here, and then 5 to the n. And then now I could use n is equal to 0, because that will give me what I want.